There we go. So I know it's been a long day, but here we go. Last talk, unless you go to Ivy's talk. So yeah, so I've got probably the longest title, at least certainly the longest printed title, I think. So let's go with the quantum state smoothing cannot be assumed classical as the short version. So I'm at Griffith University in the Centre for Quantum Dynamics, which is here in Brisbane, Australia. This work is also part of the Centre for Quantum Computation and Communication Technology in Australia. So this work was done with two former PhD students of mine, Kian Laverick and Prahlad Varshavsky, and a former postdoc of mine who's well known to some people here, Arya Chantasi. And yeah, so Arya is now in Mahidol University, and for fun, I put up my Chapman affiliation. Yeah. Okay, so yeah, compared to some people in this room, I was rather late to the party when it comes to weak values. So my first paper on that topic was in 2002, which I wrote when I finally understood what weak values were in terms that I understood, which was correlation functions in quantum optics. But since then, I've written, a whole bunch of more papers on weak values and really come to appreciate them. But anyway, yeah, so I was late to that party, but I'm very glad that I was not too late for this party. And yeah, so Yakira's not here, but A and V are in the room. So happy 35th birthday to AAV. Weak value paper, and happy 90th for Yakir, and I'm sure he's taking a well-needed break right at the moment. Okay, also, so before I actually get started on the topic, some things I could have talked about, but didn't, just in case people want to ask me about them. So one which I'm quite excited about is some work to do with Wigner's friend, and so we just had a paper accepted to Quantum on this. This is the last in a series of papers on this topic. And I guess one reason I wanted to put up on this, so I'll tell you, okay, a thoughtful local friendliness no-go theorem, a prospective experiment with new assumptions to suit. And basically what this is all about is doing an experiment with a quantum artificial intelligence, so running on some enormous quantum computer. And the main take-home message from this is that one can get an exponential improvement in the names for quantum artificial intelligences beyond Quintelligence or Compute or Charlie, by using the name Quali, which is what we do in this paper, which, okay. And the other things I could have talked about here, which would have been very suitable, which is some very recent works on weak values with Ephraim. And I thought Ephraim might have talked about this in his talks, but as it turned out, no. So, but you could ask either of us about that. Okay, so so I am going to talk about something to do with quantum state smoothing. But to begin with, I'm going to motivate what I'm going to talk about. And so important to note that what I'm starting with is not quantum state smoothing, which is a thing that I invented basically. And we'll get to what that is by part 2 of the talk. Okay. All right, so yes, so motivation. So I'm going to begin with purely classical theory, and which is going to explain where this term smoothing comes from. It comes from classical estimation theory. Okay, so we're just considering we're going to estimate some classical variable at some time tau. Obviously there are many ways of talking about an estimate of a variable. One could give, the mean, the mode. Oops, I don't know. That was not deliberate. I don't know what that's going on about there. Anyway, there are different ways one could come up with an estimate of some classical thing, but all of them could be obtained from just saying, well, this is my entire probability distribution, which is describing my knowledge of this classical quantity, okay, this P of xi. And from that, whatever type of estimate you want, you can get from this probability distribution. So the modern way of thinking about estimation is just give me the probability distribution, and then from that you can obtain anything. Okay, so given that there are still different types of estimates one can consider what's called in the engineering literature filtering, which means take the information I've obtained up to time tau and construct the estimate from that. Okay, that's yeah, so that's what this picture is meant to represent, and I should say this is taken from a paper by Mankate-san, or adapted from it anyway. So yeah, so filtering is just writing down a condition probability distribution. So this subscript F is for filtering, which means conditioned on the past measurement record. So whenever I've got a thing with a leftward pointing arrow, that means information in the past. Okay. On the other side, I can consider retrofiltering, which is all the information which is obtained after the time of interest. And this is, well, I'm going to use this notation for obvious reasons when we get to the quantum case, to indicate, in this case, we're talking about the probability of getting that measurement record, given that the system parameter really was xi, say, at that time. And then I can consider putting them both together now, and you'll see why I wrote it this way rather than with the probabilities the other way around, is that if I now want to just talk about the probability distribution conditioned on the entire measurement record, I simply multiply these two things together and normalize them, and then I get this, yeah, that's exactly what I just said. I get the entirety. I should keep track of that. Okay, so that's classical smoothing. That's what smoothing means. Sometimes it's called that this is causal estimate and this is an acausal estimate, but I'll use the terms filtering and smoothing and retrofiltering for those. Okay, so that's classical. What about in the quantum case? Well, there's sort of an obvious analogues for filtering and retrofiltering. And so, for example, in this paper by Klaus Molmer and colleagues, they introduced well, they don't introduce these concepts, but they introduce the idea of putting those two things together and calling it something. They called it a past quantum state. And they just said a past quantum state is when you have both rho f, which is the state, the filtered state, the state conditioned on the measurement results in the past, and a POVM element, okay, which is the analog of that classical probability distribution of the outcome given the system configuration. In this case, it's just a positive operator, and the trace of that with the state gives you the probability of a certain outcome. So in this case, yeah, so this is a positive operator, which depends on the entire future measurement record that you might be measuring. And yeah, so that's normalized in some way like this. Okay, so I'm sure everyone in this room, even if they can't quite read the grey stuff on the left-hand side, are probably saying, this looks eerily familiar, this idea of something from the future and something from the past, and putting the two things together. Because yes, of course, this is a very old idea, going back to the work by Yakir and colleagues in 1964, and more recently with Daniel Rohlich. There's so they call it a two-vector formulation of quantum mechanics. So yeah, so in general we could call this a two-state formalism or two-state vector formalism, depending what you want. So yeah, so the special case which was considered over here is when your pure state, when your filtered state is a pure state, so you have some initial preparation in a pure state, and it evolves unitarily up to time tau. And the retrofiltered effect would be your projector onto some final state, which is evolved backward in time from time capital T to that time tau, which you're interested in. And you put these two things together, and you could call it, yes, a two-vector formalism or past quantum state or whatever you want. All right, so that's analogs for filtering and retrofiltering, but what about smoothing in the quantum case? Well, naively, you might think in the classical case, since you just multiply those two things together to get the smooth quantum state, that in the quantum case, why don't we just do the same thing? Multiply these, they're both positive operators, multiply them together, should be a positive operator, right? No, because if these don't commute, then this thing is not Hermitian, let alone positive in general, okay? However, that doesn't mean that it doesn't have any meaning, because, again, so this is the paper by Bankei-san, which I talked about before. if you do calculate this thing and imagine that it is a state and use it to calculate expectation values, those expectation values are exactly correspond to the weak values as introduced in this other paper by, the people, AAV as I mentioned before. Except, again, in this paper, it's all done with pure states for the initial state and the final state, but it's exactly in the generalization to POV mixed states and POVM elements is the same. Okay. So I think that's what I said there. Okay, so we can interpret this in terms of weak values, but we can't really think of it as it's not a state in the normal sense that we have. Whereas in the classical case, we always just get something that I can think of as a probability distribution in the same way, whether it's smooth or filtered or whatever, it doesn't matter. But in the quantum case, no, this has this very particular interpretation, but it's not generally a state. However, okay, if these things do commute, if it so happens that the POVM element and the retrofiltered effect and the filtered state, if they commute, then if I multiply them together, I do get a perfectly good positive state. Okay, if I multiply them and normalize it, then I get a state, what I'm calling this naive state here, which is Hermitian and positive. And so everything seems to be fine. Okay, that this would be a way to define a smooth quantum state. So let me state that again, the obvious. Okay, if these things commute, then there is a basis, okay, for my quantum system such that I can write the effect and the filtered state as just mixtures of this, projectors onto this state. And my smooth state will also just be a mixture of these states. And to calculate this probability distribution appearing here, these diagonal elements, I just use the same way that I do it in the classical case. I just multiply these probability distributions together and normalize it. And right, this is not just a theoretical idea. This has been used a number of times in experiments. So cavity QED experiment from Mabuchi lab, 2009, atomic jump experiment, if you like, from Machede's group, and another cavity QED, but in microwave frequency from Serge Roche and Dotsenko group in Paris. So it's an obvious idea and obvious enough to have been adopted in various experiments. So but that's not the end of the story, okay? If that was, that would be, this is just the start of the story because, all right, the main point of this talk is to say that yes, if these are satisfied, then this is a way to generate a smooth quantum state in the sense that it is just a single state, as in the classical theory. It's not a pair of states. It does have the property that if I think of this as a state conditioned on both the past and future record, if I average over the possible future records conditioned on the state at the time tau, and use that to average over all the possible smooth states that I would have by the end, I do just get back the filtered state. Okay, so that's sort of what you'd expect. And of course, it's a genuine state. It's positive and Hermitian. So it's a smooth quantum state, but the main point I'm going to make is that it's not the smooth quantum state, okay? In the sense that there's a more general way to define a smooth quantum state that satisfies these three conditions. Whoops, oh well, that's going to happen. That satisfies these three conditions, and it only reduces to this quantum state with an extra assumption. Was there a question? Yes, let me just finish the slide. Yeah, with the extra assumption that the true state, which I'll get to, is diagonal in this same basis that I'm using. I should have said that I welcome questions at any time. So yes.
I just got caught on your claim that if you take this state and average it over all the possible future measurement records,
right,
you get back the other state. Because in what sense do you need average if you want to get a pure state at the end? How do you average coherently over the different measurement records?
So there's no pure state at the end. I'm not sure. Yeah, what do you mean by at the end?
I misunderstood what you said. I thought it is if you average over all possible future measurement records,
Yeah.
the state you end up getting is the same as the initial state, just propagated forward.
It's so maybe let's go back to the I don't know somewhere. So in the two-state vector formalism or the original weak value formalism, yeah, you just have some pure state at the initial time. It propagates forward unitarily, and likewise you have some projection at the end and propagate it forward back, propagate that back unitarily. The situation I'm considering is that you're continuously getting information about the system. You start the system in some mixed state, and then you're getting information about it, and then you say, okay, this is the time I'm interested in. But then after that, you also continue to get more information, and you could also be losing information. So it's all completely general, and there's no purity, built in anywhere to the.
But I could take a special case of your example.
Ah.
That mixed state at the beginning was completely pure.
Yeah. Okay. So the special case.
All measurement records, how am I ever going to get that pure state back?
Yeah, okay, so very good question. And do I make a particular comment about that? I think okay, but I think maybe a comment about that later. But if everything is pure, then it turns out I'm never going to do better than just using the filtered state. So it will average over it trivially in the sense that all the smooth states will just all of them equal to the filtered state.
No, I'm just saying the initial condition is pure. But
Yes.
Still different possible measurement records because you're not measuring
Um,
in that basis.
Okay, but I thought you were right. I thought you were saying that the filtered state was pure. Yeah, because I thought that's where your puzzle was. How could you end up with a pure state if you're averaging over different possibilities? And the answer is that if the filtered state is pure, then that's basically saying you have as much information as quantum mechanics allows you to have about the system. And so getting future information doesn't add anything to it. So in fact, your smooth state is always going to be the filtered state in this case.
I see. Thank you.
Right.
So, if you allow questions, sorry,
Yeah.
to make kind of completely naive. And for me, classical state is just a point. Probability distribution,
Yeah.
I don't think they exist in nature. So, what is genuine state? I don't understand. Probabilities, what it is?
Okay. So here, these are quantum states now. These are now all quantum states.
Quantum state for me only in pure state.
Oh.
If it's density matrix, I will always
All right.
purify it and when
All
I
right.
say it's
Okay.
part of the entangled state.
All right,
I don't
okay.
understand state which is not.
Okay, so I'm using state in a sense which encompasses mixed states, and in the classical situation encompasses probability distributions. So this is a quite common terminology in engineering. I know it's probably less common in physics to talk about a classical state, to talk about a probability distribution as a state in the classical case. But yeah, in the context where you're really thinking about, well, what do I know? What's the information I have, and what does that tell me about what's out there in the world? The idea of a state describing that makes sense in being a word which one could use for both mixed states and for probability distributions. So in any case, that is how I'm using it. So that's what I mean by state. Yeah.
So in quantum language, it's the density matrix of
Single system. Yeah. But it's describing what I know about.
so it's not really.
Things.
It's only what you know. It's
Yes.
not what is really there.
Yeah, but we'll get to what's really there in a minute. Okay, so pure states
Your
will.
Information. Your
Yes,
state is
you
your
could-
information.
yes.
It's not a state. It's just your knowledge.
It's an let's call it an information state, which is sometimes used. That's a term that's sometimes used. Okay, all right. But true states are going to come into the story Yeah, we'll get there. And in fact, I think we're on to, okay, it's just describing, so what do I mean by quantum state smoothing in this general sense? So the background, again, to be more explicit about what I was saying is that I'm thinking about this in the general context of an open quantum system. So it's continually leaking information into the environment. And if I just allow it to do that, then my information state, if you like, I'm going to take it to be describable by, its evolution to be describable by this master equation, okay? So this is a Hamiltonian term. This is what are known as Lindblad terms. It doesn't really matter what they look like. The point is this is a standard a Markovian equation to describe this. Okay, so that's going to produce a mixed state even if you started with a pure state, but that's because you're losing information or the system is becoming entangled with the environment. And the point about a strongly Markovian system like this is that one doesn't have to just let that information propagate away. One can actually grab it, turn it into classical information if you like, by doing measurements on the environment. And one can do that in a way, like in basically continuous way in time without invalidating the master equation. So nothing I'm doing here is talking about going and intervening on the system. The system is always going to be, on average, obeying this master equation. Okay, well, a master equation of this form. So I'll call this continuous measurement monitoring. Sometimes it's, to get that idea across. So monitoring can yield information about the system so that in any individual run of the experiment, the conditioned state of the system, which is exactly what we call the filtered state of the system, will differ from this master equation solution and typically will be more pure. So it's a function of the past measurement record, so that's just some stochastic thing happening in time. And so the filtered state is a thing that's going to evolve stochastically in time. But on average, if I average over all the measurement records that I could get creating that filtered state, I will just get back the solution of the master equation. So this more mixed state rho of t, which is the solution of that equation there. And a very important thing that's going to come up later in the talk is that different ways of measuring the bath can give different types of information about the system, and so you get quite different behavior for rho f depending on how you measure the bath. Okay. All right, so with that general context, then this is a picture explaining what quantum state smoothing is, as my student Yvonne Guevara and I defined in this paper in 2015. So we have, so here's my system, an open quantum system leaking information into the environment. I want to consider two parts of the environment, one which Alice here has access to and another which Bob has access to. And Alice is going to be basically the person that we're thinking of as our primary observer. And so the filtered state is the state that she calculates, right? So it's her information state that she calculates as conditioned on her measurement record O, that's what we mean here, up to the time of interest t. Okay, so that's just something which Alice calculates as a description of the system here. Let's imagine that Bob, as well as getting his measurement record, that he also gets whatever Alice gets. So everything gets handed to Bob just so that he has complete information then about the system. And so his conditioned state we could think of as being the true state of the system, because we can basically just always take this to be pure. We could say, let's say that Bob has access to everything, so that's always a pure state. Nobody could know more than that. And so assuming that everything is accurate in the experiment, this we could take to be the true state. The smooth state now is what Alice, the point, as I said before, if the filtered state were pure, then there's nothing more Alice can do, right? She can't get a better estimate than a pure state for a quantum system, because a pure state is as good as possible. But if she's missing information, right, then, which she is, if Bob is getting some of it, then by considering her future information, the information she gets after time t, she could say, does that let me estimate or guess what Bob saw better than just looking at the information up to time t? And the answer is that yes, it does. Okay, so Alice's filtered state turns out that, yeah, we can just think of it as, well, that's the state that Alice calculated by the usual way of the state condition on her measurement record. Turns out that's exactly the same as if she'd imagined that there was a pure state and then averaged over the unknown record. I should have said O stands for known. Oh, sorry, no, it doesn't. O stands for observed. O stands for observed, and U stands for unobserved, but that sort of. Let's say unknown because it's unknown. Obviously, it is observed by Bob, but it's not observed by Alice. It's unknown to Alice. If she averages over the possible unknown records, unknown to her, up to that time, conditioned on what she has seen up to that time, it doesn't make any difference. She gets back the same as normal quantum mechanics. On the other hand, if she does it conditioning on her entire record, both the past and the future of the time of interest, then she gets something which is non-trivially different. She gets a smooth state because it's now the state at time t conditioned on both what she saw before time t and after time t by averaging over what Bob might have seen up to time t, right, of the true state, but now conditioned on what she sees in the future. And on average, this is a better estimate in the sense that if I have time, I'll get to. It's closer to the true state than the filtered state is. So that's the idea of quantum state smoothing. Okay, so I think this is just, yeah, everything which I just said, but yeah, in more detail. So yeah, you could say that what Alice, if you want to give it an informational definition, what Alice wants to know is what's in the mind of Bob, okay? And you could think of, yeah, anyway. In the original paper, I think we had God in there, and then the referee or the editors or someone didn't like any reference to God appearing in physical review letters.
So that's the right way to do it. You should have Alice, Bob, and God.
Yeah.
That's the right way to do it.
Yeah. But anyway, so we just, okay, so Bob is the stand-in for God. So Bob knows everything. Alice wants to know the mind of Bob. So yeah, she wants to make her best guess as to what Bob knows the actual true state to be. And yeah, so yeah, okay, there's an equation given that. Yes, she wants to average over what, oh, hang on. Oh yeah, no, that's just saying that's the filtered state. Okay, as again, this is everything which I just said on a previous slide, so I'm not going to say it again, right? But the difference with the smooth state is that she's now averaging, this probability she's averaging over conditions on the future as well, and that's a better estimate. So the average, we can actually work out the expected purity of a conditioned state, it turns out, is exactly equal to, if it's an optimal estimate, the way we're doing it, is equal to the fidelity of that state with the true state. So if we end up with a pure state, and we've done it in this sort of correct way, which I'll explain later, then the average purity is actually a measure of the average fidelity with the true state. Okay, so the important thing is that the filtered state, as I said, thinking about that as being an average over the true state doesn't matter how Bob unravels his path. Okay, we always just get back the filtered state that doesn't, might imagine that Bob doesn't even exist. Whereas the smooth state, it does depend on how Bob monitors his paths. And that'll be a crucial thing that will come up later. Yeah, okay, and here's the answer to Ephraim's question, is that the smooth state is not equal to the filtered state only if the filtered state is not pure. Okay, yeah. And that's also true for classical smoothing. If you have a delta function for your filtered state, then you can't do any better than that by having more information. Okay, so then this is the paper, which is on the archive, and then this is a summary of the main results in that paper. So again, we're considering this situation where, from the point of view of filtering and retrofiltering, everything looks classical. Okay, so the filtered state and the retrofiltered effect are co-diagonal. Okay, they're commuting. So then the first result we show is that if it is the case that the true state is also just one of these states in this diagonal basis, then it is indeed the case that the smooth state is the classical smooth state, if you like, that it's just what you'd expect by multiplying these probability distributions, and then it's in the basis. In other words, everything looks classical. However, right, so that's result 0, if you like. Result 1 is that if this condition doesn't hold, if the true state is not one of these states, then the smooth state is not necessarily equal to the classical smooth state. Result 2, in fact, the smooth state need not even be diagonal. Okay, so even though as far as Alice's measurement is concerned, everything looks diagonal, the filtering, the retrofiltering, it's all diagonal. Nevertheless, Alice's best estimate of the true state may be non-diagonal. And then the third one, I'm probably not going to have time to talk about. It's a more subtle one to do with cost functions. We'll see how we go, whether I get to talk about that. Okay, and the nice thing is that we can show all of these results with an extremely simple system, which is a qubit or two-level atom. So here's our two-level atom. It's an extremely boring master equation. It's just we have rates to go up and rates to come down. Okay, so this is the lowering operator, so this is the relaxation rate from level 2 down to level 1, and this is the excitation rate to go up the other way. Now you might wonder, why does it look like a 3-level atom? That's because we want to arrange the bath, these couplings to the bath, so that we could keep track of these jumps. Okay, so the spontaneous emissions, which is this one at rate delta going here, and this one at rate gamma going here, that's just normal spontaneous emission, but I want to do the excitation via another level so that when the atom goes from the ground state to the excited state, it actually emits a photon as well, which I could then detect. Okay, so I can know when the atom is going from the ground state to the excited state.
Howard, can I ask you a question?
Yeah. Okay. Yep. We'll see whether it's the same one that Justin was just about to ask. But go. You go. You go.
I'm just going to go. Just to back a moment, because we talked about if you have a pure state and you have optimal filtering, then future knowledge doesn't give you any advantage.
Yeah.
And I can see that point. I just wanted to have you make a point of contact for the other people in the room that are familiar with this two-state vector formalism, because in that point of view, you have this past state and this future state, and you're doing this continuous diffusive monitoring continuously.
Or whatever. Yeah, it is. Yeah.
Imagine it in the simplest case where you just have like one sort of intermediate strength measurement, you would have a past state and the future state, so you carry on these two states. Whereas, are you thinking about you carrying around the entire measurement or the entire quantum trajectory? If you just make that point a little more clear.
Yeah. Okay. So yeah, fair enough question, because I sort of said, okay, if it's a pure state, then there's nothing from the future can make any difference. Obviously, that's not the case if you're going to consider a weak value or something like that. Yeah. So, or indeed doing any sort of unknown intervention in the system, and yeah, then you actually do need to carry your information from the future and your past. Okay. In this situation, so I guess two things are different. So one is, so I'm just assuming there are no other measurements going on. This is the entirety of everything that's happening with the system. But also, I'm also just trying to be more conventional and saying, yes, I mean, I know the two-state vector formalism or the past and future state formalism is a useful way to think about things in some circumstances, but I'm looking for something directly analogous to the classical theory of smoothing, where you don't have to carry two things around. You just have this one thing, which is your smooth state. And so that was the motivation for developing this, was to get something which looked like the classical formalism. And in that case, yeah, all of the things, so hopefully that's useful for other people as well. Yeah.
Thank you, Howard.
Yeah.
Wouldn't you have some problems with selection rules on that?
Oh God. Ephraim, would I?
I'm more concerned about the other point, because then if you say as long as you know no other measurements are going on, in which case this is kind of a fictitious story we can tell ourselves, but has no predictive power if it can't explain anything except the measurement record on which it was already predicated.
Well, whether it has, the fact that we're using future information always is a bit of a problem with talking about prediction. but maybe that's not what you mean.
That's the thing about weak values, right? I would better understand that, fine. But what I mean is you can't use this state to say that if someone told you, oh, actually, I was poking at the system at those intermediate times.
Yeah.
And you told me what I would have seen, you'd have to say, oh, no, if you poked at it, I can't tell you anything.
No, that's right. Then it would be different dynamics, and I would be solving a different problem. That's right. That's right. But what I can tell you is, well, we'll get to putting Alice and Bob in this picture in a minute. But yeah, what use is it? Is Alice, like Bob could basically say, well, I know what the state is. Do you? And Alice has to try to come up with her best guess. Right. Yeah. Justin, yeah, did you have a?
I figured out my question. I was going to ask why you had two decaderants.
Right.
One goes left, one goes
Yeah,
right.
and very soon, yeah, okay. Okay, so yeah, so forgetting about practicalities of exactly, I'm sure there's some two-photon transition or something you could do to make this work. Okay. Do we get a photon out when the system goes up from excited to the ground state? Right, so yeah, that's going to go towards Alice, and these are going to go, are going to go towards Bob. And yeah, for the rest of it, I'm going to consider a situation where this rate is very small. So this is just to make things elegant, because we can do everything analytically. If we take actually the amount of information going to Alice to be extremely small, so almost everything is going to Bob, but you'll see why that makes sense in a minute. And I'll also take the atom, I'll also take this parameter epsilon to be relatively small compared to gamma. There's just technical reasons for that later. So the state is actually, the steady state is actually fairly close to the ground state. And it's obviously just a mixture of the ground and excited states. Okay, so so also we're just going to take it very simply that Alice just counts photons. So the photons that come down here, she counts. Because I'm going to take that rate to be very small, overall the whole thing is extremely boring. Alice is getting almost no information. So the interesting thing only happens in the region when Alice actually does get a click. So I'm going to always concentrate around this point, which we'll nominate as time 0, where Alice happens to get a click. Okay, and then what does the filter state look like? Well, up until the time she gets a click, it's just the steady state, and then when she gets a click, of course, it goes to the ground state, and then relaxes back to the steady state. So just that blue curve there. And that's what those equations say. Now, what about the smooth state? So again, doing this classical smoothing or naive smoothing, we just take the filtered state and the retrofiltered effect. And what does the retrofiltered effect look like? Well, in the, where are we going? So after that click is basically just the identity, or identity over 2, because it's saying, well, what do I know from the future? Well, the future, as far as Alice is concerned, is whenever the next jump happens, which is, somewhere over there. Right. So basically here, it's just the identity over 2, whereas prior to the jump, when a jump has happened, Alice knows that immediately before the jump, the system must have been in the excited state, and then that, as you go back further in the past, that decays towards the identity over 2. Okay. So that's what those things are. If you care to look at them, you multiply those two things together, and you get this green-shaped curve here. Okay. So basically, after the jump, it's identical to the filtered state, but before the jump, well, at the moment of the jump, you know that it's the excited state, but then it decays, as you go back in time, it decays back towards the steady state. And so that's exactly what classical smoothing will tell you about this problem. Okay. So that's the naive thing. And moreover, we can derive this from the quantum state smoothing theory, which I explained to you before. If I now take Bob's record to be exactly in a record of these jumps, which always take the system between the excited state and the ground state. So Bob has one detector to detect these types of photons, which is an upward transition, another detector to detect these types of photons, which is a downward transition, and then the true state then is always going to be either the ground state or the excited state. And if Alice tries to guess the true state as well as she can, it turns out to come to be, not surprisingly, the classical expression for the smooth state. All right, so that's sort of the boring result 0, that we can just get back the classical result. So the first interesting result is that we don't necessarily get that back. And that we can see by considering a different type of measurement for Bob. And so this is where the diffusive measurement is going to come in. So instead of just counting the photons, let's say that Bob does homodyne measurement of the output here. So he interferes these fields with a strong local oscillator at a beam splitter and detects these outcomes here. And yeah, that's his measurement record. In this case, it turns out that the true state, instead of just jumping between the excited and the ground state with the right phase for these local oscillators, actually undergoes diffusion on a great circle of the Bloch sphere. So in this case, I've chosen it to be the y=0 great circle. So it's sometimes it could be the ground state or the excited state, but mostly it's just some other state on this great circle. And so we're going to assume that Alice knows this. Alice knows what measurement Bob is doing. And just to emphasize again that no choice that Bob makes here changes the average evolution of the system at all. So the system still, on complete average, is just behaving according to the master equation. And just in terms of filtering, it makes absolutely no difference for Alice. But for smoothing, it does make a difference. Okay? So now the smooth state that Alice has to do is conditioning on, like working out the average true state, but now conditioning on the unknown record that Bob has, which is this record of a diffusive unraveling. Okay, so these are Wiener processes. The details aren't that important. It turns out that when she does this average, we can work this out almost exactly. Numerically exactly, basically. You get a mixture of the excited state and the ground state as the smooth state. But you see, it's a different mixture from the case when Bob is doing photon counting. So it doesn't go anywhere near up to the excited state. It goes up a little bit just before the jump, but not all the way to the excited state. So it's different from the classical result. Yep.
Yeah, may I confirm that's the situation? In the Bob now is performed as the phi zero, that's the homodyne measurement.
Bob is now performing homodyne.
Bob is now in the phi zero in the homodyne measurement.
Phi, is this what you're asking about?
Yeah.
Yeah, was that your question?
Yeah, then that's the Alice knows mean on that what kind of information?
What does Alice know?
Yeah.
Okay, Alice knows what type of measurement Bob is doing,
Yeah.
but she doesn't know anything about his results.
This is term on the classical information such and so on. That's Bob sent to Alice.
Okay, so the fact that he is doing homodyne measurement with a particular phase is just classical. Yes, he's being nice to Alice and at least telling her what type of measurement he's doing.
Oh, okay.
Yeah. Thanks for asking. That is a crucial point. Yeah, she would not be able to calculate this unless she knew what Bob was doing. Yeah. Okay. Okay, so we get something different. So we don't always get the classical smoothing. And that's just a formal statement of that result. So we call that theorem 1 in the paper, that just the fact that the retrofiltered effect and the filtered state commute does not mean that you get the classical filtered state back as your best estimate. Yes?
And Howard, can you just give us a simple interpretation of the results you go back to?
Yeah, like why does it look like that?
Yeah, why is it
I'll get that. I'll do the next example and I'll put them all together. Yeah. Was that also?
My question was, what is the true state in that case and which one's closer? Meaning, if you take all of Bob's information, get the true pure state, which of those two curves, red or green, is closer to the true state?
Oh, well, I mean, the red and the green should be closer to different types of pure states, right?
Right, but there's exactly one true state in this case because Bob's doing the homodyne.
There are infinitely many possible pure states because Bob is doing homodyne, because we don't know what the record is. But we can definitely say that this is the best estimate, this is the best possible estimate that Alice could do of that pure state.
Okay, so that's the claim. The red state is
Yeah.
fact, on average closer to the true state, including all of Bob's information.
Yes.
This measurement.
Yes.
Okay.
that's right. And again, yeah, if I get time, I can even be quantitative about that. Okay, so result 2 now is the even more surprising one, but to prove that, we have to allow Bob to do a very exotic type of measurement. So it's a particular adaptive interferometric detection. So it still involves interfering with the local oscillator, but now it's actually going to be a weak local oscillator. And the amplitude of that oscillator has to be adapted depending on the previous result that Bob gets. Okay, so it's not easy to do. And no one's done an experiment like this. I'd love someone to do, because there's some beautiful things which you can do when you have measurements like that. And so I have papers about this. So in particular, what Bob can make happen in this situation is the system can be forced to only, so remember, in the first case when Bob just detected photons with no interference, the system just jumped between the excited and the ground state. And given what the master equation looked like, you'd be forgiven for thinking that's the only way to make Bob's state just jump between, a couple of states. But no, by doing this incredibly complicated thing, Bob can actually arrange that the atom jumps between exactly 3 states, which are on this great circle, this y = 0 great circle. None of them are the ground or the excited state. They're these 3 states here. And basically, it just jumps cyclically between them. So every time he gets a click in either of these detectors, it's pretty weird, wherever the state was, it jumps to the next state and then stays there until he gets the next click, in which case it makes another transition, etc. So it just keeps going around this triangle, and there's no way I'm going to be able to explain how it's possible to do that, but you'll just have to trust me that it is, and the particular, this paper here has the particular scheme. I think I won't bother about that. And maybe you can guess where it's going from this picture, but we'll see. Well, there it is there. Okay, so just as in with scheme 1, Alice, when she gets a click, that only gives her information about sigma z, about the excitation, because the only thing she gets is, well, if I got a detection, it was more likely to be excited than not excited, right? That's the only information she gets from her click. But in this case, knowing that the state is more likely to be excited actually tells her something about the value of sigma x. Okay, because if the state can only be in one of these 3 possible states, and Alice knows that it's more likely to be excited, she also knows that it's more likely to have a negative value for sigma x. And so in this case, the smooth state that she reconstructs is not diagonal in the sigma z basis. It actually has this non-zero sigma x component, which you can see here in this, so this is 0 here. So as you get towards the click, the smooth state has this negative, it picks up this negative x component. So what am I looking at here? So it's plotting that. The other thing which was plotting is the length of the block vector in all 3 cases, just showing that, they're all quite different in their behavior. Okay, so that's the main point. That's theorem 2, is that, even if these things commute, that doesn't even mean that the smooth state need commute with either of them. Okay, so here's the explanation of, sort of what's going on. So in the first case, the simple case where Bob's condition on Bob's result, it really is just jumping between excited and ground state. This is a fairly long time before the click. So this is more or less the steady state. So it's mostly in the ground state, a little bit of probability in the excited state. In the homodyne case, it's spread all over, but just because the damping is stronger than the excitation, it turns out that most of the probability distribution is down the bottom here, but it's symmetric around like plus and minus x. Okay? And then here are those 3 states that we got there. So in this case, conditioning on the fact that there will be a click in the future makes almost no difference, because I'm a long way away from the click. So 3 time units, 3 decay times. So all of these average to almost the same thing, and they almost all average to just a steady state. But as I get closer to the click, so this is just minus 0.08 time units away from the click, where gamma equals 1, I think. You see, now you have very different smooth states. So in the case where it's either excited or ground, now Alice is very close to certain that it's in the excited state. In the homodynamic case, all that's happened is that this distribution has got pushed up a little bit, like the ground state is now very unlikely, but it's still mostly down here in the bottom half of the Bloch sphere, so her smooth state is there. And as I said before, in this weird thing where you're only ever in these three states, if you think you're more likely to be excited, now you actually think you're pretty likely to be in this state here, and the average turns out to be over there. So that's how you can get these weird states coming up. Okay, I don't know, have I got time for a, yes? Okay, I can't remember where I started. All right, so to get down to this question of, like what is the actual best estimate and in what sense is it best? So let's just go back to the first case to begin with, the simple case where Bob is just doing photo detection. So what do I want to say? So in this case, remember, so the filtered state before the click is just this steady state, right? Because Alice doesn't know anything, and then she gets a click, and then it changes to, then it changes to the ground state. And so what I'm plotting here is the purity. So the purity for the filtered state is fairly close to 1 because the steady state is fairly close to the ground state. And then it jumps to the ground state, and so it goes to exactly 1 and then decays back. Okay, so that's. Whereas the smooth state, right, it starts being fairly down near the ground state, but then as it gets closer and closer to when the click's going to happen, it gets closer and closer to the excited state and actually hits it at the point when the detection happens. But that means that it goes through the maximally mixed state, right? It goes from being close to the ground state to being up at the excited state. So the purity of the smooth state actually has this great big hit, goes down to the minimum value 0.5 before it starts to go up again. And so you might look at that and say, well, that looks like the smooth state is a worse estimate because it's less pure. So we're getting this weird thing that the purity of the filtered state is bigger than the purity of the smooth state, even though we can actually say that the purity of any state is the fidelity with the actual true state. So what does that mean? Does that mean that the smooth state is a worse estimate? No, because all of these estimates are defined using a cost function which is not fidelity, but rather trace mean square error. Okay? And you can say, well, why choose that cost function? Well, essentially because that's what you would choose in the classical case if you want to get the standard classical probability distribution. So basically mean square error is your standard cost function for estimates to correspond to like what a standard Bayesian estimate. So that's what we've adopted here. And if we hadn't done that, we would have got completely different results even for the filtered state. It would just be very different from standard quantum mechanics. So so that's the answer to the question, is that we're not actually trying to maximize the fidelity. We're trying to minimize the trace square deviation. And if I plot that, I can actually work that out, and it turns out that in terms of the trace square deviation, the smooth state has a much smaller cost function than the filtered state. And so that's cool, right? So it actually all does make sense. So even though the smooth state is less pure, it's a better estimate in the sense that we want it to be. Okay. But now I can ask the question, well, what about the various other estimates? So they're all estimating different true states now, all right? So that's right, different true states conditioned on, but they're all now going to be conditioned on the same thing. And I can just ask, well, which of them is best at estimating its particular possible true states, depending on what Bob is measuring. And it turns out that the classical smoothing is not even good by that measure. Okay, it's actually most of the time the worst of all three. So these are cost functions, so small is good. And so the classical one actually looks pretty bad. So it's still right, this is the same curve as down here, so it's much better than the filtered. But when I compare it to the homodynamic case or this weird adaptive measurement case, they actually do better, except for immediately before the jump, because that's when, in the classical case, you know that it's an excited state, which is pure, and so you can never do better than that. So I think I've just said everything I've got there. So does that help? And
Yeah, the immediate follow-up question I have is that this minimizes this mean squared error thing, which is kind of funny, or differencing density matrices. If you use something like infidelity,
what would you get?
Different norm, you get a different smooth state.
You do, but you also would get a different filtered state. That's the weird thing. And it turns out the answer to what would you get if you use fidelity is actually very easy. You would get, you calculate exactly what you would calculate using this measure, which gives you a mixed state in general, and then you just project, okay, so in the qubit case, then you just project it to the surface of the sphere. Because basically fidelities are always higher when one of your states is pure. So so everything, so that's what it turns out to be. And so even doing filtering, if you said, my aim is to maximize the fidelity with the true state, I would calculate the normal filtered state and then make it pure. So we call that lustrating the state.
What happens when you pass through the maximum state?
Well, there you just take a random, you can make a random choice and it wouldn't matter. Yeah.
Okay.
Yeah. But I think that's right. I know this doesn't look that obvious, like why would you do that? But if you choose something else, in general you get something different. There are other choices like the relative entropy also gives you the standard estimate. So this is not the unique cost function which gives you the standard one. But there are definitely some cost functions which don't, like the fidelity. Okay, so that's the conclusion. Well, that brings me to the conclusion. So to reiterate, I started with the classical case, just to emphasize that there's no real difference conceptually in the classical case between filtering or smoothing. It's just conditioning on, are you conditioning purely on the past or are you conditioning on things in the future? And then in the classical case, this is just the product of the retrofiltered effect and the filtered state. These things, these individual things have obvious analogs in the quantum case, but the obvious analog of the smooth state of multiplying this doesn't work, except when these commute. And so you'd think that, oh, well, if they commute, then everything's good, we're back to the classical state. But then we had these results. That yes, we can derive this naive, if you like, smoothing formula from the quantum state smoothing theory, but only if the true state actually does commute with these things as well. If it doesn't commute with it, then it's not necessarily the case that the smooth state is this. It's not even necessarily the case that it's co-diagonal with the filtered state and the true filtered effect. And it doesn't even necessarily have the lowest cost function out of the possible types of true states which we're trying to estimate. Okay, and then I think just to throw up, there's a whole bunch of work. This is not all of it, which past and future work going on in quantum state smoothing, I guess I wanted to put this last one up, which is a future work, just in case there is a conference proceedings. And then I can say that I talked about this work at the conference because the paper, the actual work I talked about, we've already submitted somewhere else. But we have another curious question to ask: is what happens if Bob lies to Alice about the measurement that he's doing, for example, or Alice is just mistaken for some reason about that? So hopefully we'll have that for conference proceedings if that's going. Okay.
Thank you, Howard.
Thank you.
So one question I had, you had this very exotic measurement scheme where you had the photo detection plus 2 homodyne measurements plus adaptive feedback. Amazing. And that was a way, as far as I could tell, to get some coherence of your qubit into the game. I'm wondering if you just thought of a much more simple way of doing it, which is simply to drive a transition between the two states and do like a Rabi drive, which would naturally bring coherence into the story. It would, but then
Alice's filtering and retrofiltering wouldn't just be this simple diagonal, right? So the trick is to have the complete dynamics of the system look classical in the sense of it's just jumping between the excited and the ground state, right? And as far as Alice is concerned, because he's just detecting these, that's all that's happening. But somehow we need to get coherence in, but not by actually altering the system in any way. So maybe just to emphasize that the feedback. Oh, that's not actually that one. It's the next one, isn't it? Yeah, the feedback here is not onto the atom, right? The feedback is just onto the phase and actually I don't think we need the phase. So I think it's onto the amplitude of these local oscillators which are interfering with this light here. So yeah, so the master equation for the atom never changes, and that's crucial for the filtering and retrofiltering to stay always just this diagonal description.
That's what you're motivated. You wanted to keep everything diagonal.
Yeah,
and
exactly,
see how
yeah.
you could- all right, thanks.
Yep.
In the absence of Jeff, are there any other questions? Thoughts?
So maybe just, I never understood the motivation. There is a two-state vector, it describes the whole story given information from past and future. And I think there is no hope that one state can give the same information when the two-state vector gives. So why
Yeah.
to look for it?
Yeah, okay. So there are definitely, there are instances where what you say is absolutely true. Like if it's possible that someone is going to come into your system at time t and do a weak measurement, say, then, or a strong measurement, then yes, you can't do without knowing everything that happened before and everything that happened that, and you can't combine them in any way that would obviate the need to have both of them separately. I guess I'm just considering a different situation where we're saying that's not happening. Like there's no, the measurements that are being made, everything that's happening is described here.
No.
Yeah.
No, it's, of course, what Justin said that we have the two-state vector formalism is more helpful because it allows strong intervention.
Yeah.
But I also saying the description of a system is interesting, and maybe the coupling, extremely weak coupling, which happened due to the environment. I would like to know what happened. And my two-state vector formalism, this is what my deterministic weak value, if I have complete plane post selection, tell me exactly how how infinitesimal interaction during infinitesimal time affect the environment.
Yeah.
So I don't put anything strong. So this is not an issue that strong measurement change. So if you have very weak coupling and maybe very short time coupling, so will this one vector still help me to describe? I believe that the description is how it's affect environment.
Yeah.
Even if it's effect it's very tiny.
Yeah.
So does this description?
So no, it does not. It does not replace the two-state formalism or two-vector formalism for purposes like that. And in no way was what I was saying meant to be a criticism of the two-vector formalism. So I think it offers lots of useful intuition and information, and I'm absolutely not denying any of that. I'm just saying I was motivated for whatever. Oh, okay, let me tell you what my actual motivation was. Maybe I didn't really say what my motivation was. I mean, I sort of said this is the motivation, but I never really said. My original motivation, so this was published in 2015, okay. The idea for that paper I had in 2009 when I went to a conference in Caltech and heard Hideo Mabuchi talk about this paper and put up a picture like this. And say that, oh, by the way, this, we got this trace of, which of the two states our system was in by smoothing the record, the entire record, rather than doing filtering. I was like, what? Like you're putting up a quantum state and saying that it's conditioned on future measurement record? What on earth do you mean by that? And so then that just got me thinking, so that's really the motivation for this whole work, is they wanted to explain what the hell are these experimentalists doing, right? From their point of view, what they were doing was just saying, oh, well, our system is basically classical, so we're just going to, one of the, actually he wasn't even an author, which I think is terribly unfair. The guy who actually did the theory for this plot, he was an author on a later paper. But yeah, he knew some classical theory, and he said, oh, why don't you do it this way? And they said, okay, we'll do it that way. But yeah, for me, I always want to know, well, better, more than, for them, I think, so in a sense, my motivation is that I am worried about, I'm not just satisfied with, oh, well, this is a good model for our experiment. I wanted to know, like, conceptually, what could this possibly mean? That you get more information by using future records, and yeah, that's really the whole story. And then ever since then, I've just been exploring, like, well, okay, if you have a theory like this, what are its limitations? You know, how different is it from the classical theory? Can you make it, you know, break? So yeah, that's maybe I should have said that more explicitly. Yeah.
Thank you.
Yep.
Justin?
Let me try to paraphrase your actual problem here, and I think this will help Lev as well. So I think what you're trying to do is find the best estimate of the forward propagating state.
The forward propagating true state.
Yeah.
Yeah, exactly. Yeah, yeah.
Ideally, you have a pure state that's propagating forward. And I think, Lev, you agree with this. There's the true global state. It's always pure. That's your state, right? Going forward.
There is a pure state propagating forward. Then there are all kind of measurements of this kind of intervention, and there are splitting. So the pure state
well.
for me later, it's not the pure state which it's a multiverse. So I'm not,
Okay. All right. Well.
in the future, I'm not interested in the multiverse. It's not relevant for me. For me, it's what's important, what counts in my world. So this the true multiverse. No, I don't.
Yeah.
So you want the condition state saying in my universe.
There is no such thing. It's the idea of William. I think it's a wrong idea. You cannot have this condition state.
No,
you have to take
We
both
use
of
this
them.
all the time
Well-
in weak values. You say, I see this measurement result that prepares this state. That's a conditioned forward moving state. That's pure. And I know, conditioned on the fact that I got this result to prepare my state. Now I'm going to use that as my past preparation and then construct a weak value with it. That's exactly what he's doing here. He's saying that pure state is the true state, the
Yeah.
forward propagating state.
Yeah.
But he's losing information because of something that happened over here, some environment,
Yeah.
some bomb. And so he
Yeah.
doesn't actually know this pure state perfectly. So what Howard's doing is trying to find how can he learn the best estimate of the forward propagating state that he can, given that he knows something about what happened, even though he doesn't know everything.
My understanding of our program is different. So there is this, there is a pure state, and there is a splitting, multiverse, but we live in particular world. And then there is this way to describe everything by two-state vector in our world, and this is complete story. But the two-state vector is not a good idea, we're not used to it. We want to find the best single pure forward evolving state, which is a wrong state, because the correct description is two-state vector. But this, how we can replace the two-state vector with the most closed one, the forward evolving wave function. It's not true in any way, because the true story, it's a two-state vector in our world. But for our predictions, for our practical purposes, to be engineer or whatever, this forward evolving state even doesn't exist in nature, but it's the best. It's very helpful for us in our world how to behave. Is this the problem?
Well, it is. It's very helpful for us. Okay, I know it. Yes, and I guess also for 99% of physicists, it's the only state, right? Not in this room, obviously, but.
Okay, in the interest of time, I want to go to Yutaka for the last question of the session.
Yeah, thank you so much. That's the time. In the first of all, that's the such kind of to remind it to 2009. In that I discussed with Manken-san.
Oh yeah. Because he also had. Yeah.
According to the acknowledgement, this is my name. It's written. This is because that's such kind of issue. On the left, discuss about that. In that the mathematical formulation, mathematical statement, that's quite similar, but the philosophically is different. Yeah, of course. But some of the case is that the mathematical consistency is very helpful to the smoothing too. That's I think in that some as far as I understand in that Howard motivation that Justin explained in that some of this the mathematical similarity will help. Mathematical similarity to the two-state vector formalism will be helpful to that's another kind of the scientific field. Then if that's so, I have a question to the Harvard. In now in the future state, we with the current state, we as far as we best, we
So, sorry, the future state or the
no,
smooth
the
state?
The current state, sorry.
The
Current at that time.
well, I'm trying to think where I should go. Is that a useful picture?
Yeah, just the forward state.
Yeah.
We estimated there.
So the one that Alice would estimate, for
Yeah.
example? Yes,
Yeah.
okay, yes.
In the retrocausally, in the how to do that, in the similar sense, in the smoothing technique, that's the filtering on that going back to that.
Right, the retrofiltering you're
Yeah.
talking about. Yes, yes,
Yeah, that's the both of this.
yes.
Can you consider that such kind of smoothing and the filtering?
So I'm not sure what you, yeah.
This is because that's the one state in the future going state.
Yeah,
In terms of the two-state vector formalism.
yes.
But the retrocausally is that some of the measurement outcome going back to the time
Yeah,
on what is the state is. This is the filtering. Then it might be possible to do the two concepts to jointly together.
yeah. So I would say that's exactly the
Yeah.
philosophy that Molmer has been promoting, to just say, well, I mean, I don't think he acknowledges the relation to this much older work enough.
Yeah.
But basically, it's just saying it is a generalization of this idea, but just thinking about what a particular, rather than thinking about what the world is, but thinking about what an observer knows.
Right.
And to use a forward propagating filtered state and a backward propagating retrofiltered effect, both of which are conditioned on all the information which you get either before or after that time.
Right.
So there's that idea. That's and again, I don't want to say that that's a bad idea, but I was just motivated to look at something different, which ends up like involving these concepts, at the heart of the theory. But the actual thing that I'm calculating is, as I said, is essentially a forward propagating state, but using information from the future to get a better estimate of that forward propagating state.
Yeah.
Okay.
That's great. Thank you.
Yeah,
Okay,
you're
why
welcome.
don't we thank Howard again for this great talk.
Thank you all. And just time to
Yeah, you just-
make it.